Okay, folks. Welcome to the last day. So this is it. We've got just a few more things to cover. Don't forget about your resources. Tomorrow we've got the math in almost all day, 10 a.m. to 5 p.m. I'll be there all day. It's a good time to get prep your math files. We'll have a review session Tuesday at 5 o'clock. I did send you all an email. I had to update my office hours because I've got like a graduate student thing going on Wednesday, but I extended my office hours to the afternoon. So, okay. This is a huge theorem because what it gives here is an ideal theoretic characterization of UFD. So you can do it in terms of ideals. You can talk about every non-zero prime ideal contains a non-zero prime element, and whenever something can be done in terms of ideals, that's what. Let's go through this proof of 11.7 first. Let's suppose first, R is in UFD. I want to show that every non-zero prime ideal has a non-zero element. So if I have a prime ideal, then there exists X, there exists a non-zero, X and B. It's a non-zero prime ideal, so it has a non-zero element in it. Now, I'm assuming that R is UFD, so it means that that sucker factors into primes. Right? So, of course, X is in P, so this product of these prime elements is in P. And since this is a prime ideal, and there's a product of crap that goes into the prime ideal, that means one of the elements in the product has to go in there. So, for some I, PI is in P. That's what is one. And there you go. That's your non-zero prime ideal, non-zero prime element. Right? The interesting part is that's enough. Right? If every non-zero prime ideal contains a non-zero prime element, then everything factors into primes. So let's go down that road here. Suppose every non-zero prime ideal contains a non-zero prime element. I want to show that this is UFD. So I need to show every non-zero non-unit is a prime. Last time in class, we talked about this. If I talk about things in terms of products of primes, I don't have to say anything about uniqueness anymore. Because if everything factors into primes, it does so uniquely. We had that from last time. So my burden here is to show that everything that's not zero, not a unit, can be written as a product of primes, and then I'll be done, right? So to this end, I'm going to build the following set. R such that R is a unit, or R is a product. Or both. So this is a multiplicative set, right? Because when you multiply two units together, you get a unit. So that's still in there. If you multiply a unit times a product of primes, it's a product of prime, right? Because the unit can be absorbed in primes. And if you multiply two products of primes, it's a perhaps larger product of prime. So this is a multiplicative set, right? And here's my goal. Show S is everything in R except zero. Because what that will mean is if S is everything in R that's not zero, that means that everything in R that is not zero is either a unit or a product of primes, and I'll be done. Right, okay with it? Now, S is a multiplicatively closed set. Suppose there exists a non-unit X in R such that X is not an S. So let's just suppose, for the sake of giggles, that there's an element in R. I want to say non-zero, actually. Suppose there's a non-zero element that's not an S. Now, I want to consider the following. This is really the machine that's going to make this go. I'm going to make the following. Wow. So I know that X is not in S, but I'm going to go further. I'm going to say that any multiple of X is not in S. Here's how I'm going to justify that. If not, there exists R in R such that Rx is in S. So right? So Rx is a product of primes. Now, this is impossible. And I'll justify this by induction. Show this is not possible. Inductively. So assume first well, what does this mean? Well, P is a non-zero prime, so it's irreducible, right? So this means either R is a unit, in which case X is prime, but of course, if X is prime, it has to be an S, right? So that's impossible. Or X is a unit, in which case X is also an S. So it's impossible for Rx to ever be a single prime, right? Now, inductive hypothesis. Suppose Rx cannot be a product of n or less primes. We know it can't be a single prime. Let's assume it can't be a product of n primes or right. Right. Now suppose Well, notice Pn plus one divides Rx. Pn plus one divides R, or P divides X. Right? Because it's a prime, it divides this, so it has to divide one of these two. If Pn plus one divides R, then R is R prime Pn plus one. And we can cancel. If R prime X is P1, Pn, and we apply that. And if Pn plus one divides X, then then X equals Pn plus one X prime. And now do a similar argument, because now you have Rx prime, but that's also something that doesn't intersect S, and it's the same. So this is the same conclusion. So if I have a non-zero element that's not if X is something that's not an S, the ideal generated by X intersect S is the empty set. Yes.
How did you imply the inductive hypothesis there again?
Well, because the inductive hypothesis says Rx cannot be a product of n or less primes. And now we've got this thing as a product of n or less primes.
But is that the way that you just rewrote R equals R prime Pn plus?
Yeah, this applies to any R, right? This is just what you're saying is a multiple R can't be a product of n or less primes. So here's an important step here. Does anybody remember? So here we have an ideal, and it misses a multiplicatively close set. What does that mean? You remember what we can do to an ideal? Expand it. You can expand it. We sprinkle our fertilizer on X. So X is contained, I'm going to call this an EX, prime ideal, such that EX intersect S is empty. Right? Any ideal that misses a multiplicatively close set, we can grow it to a prime ideal that misses that set. Right? Remember that one? Anybody see what the problem is? X so what was the set? Anybody remember? Problem here is, how do we define S? So we expanded this to a prime of EX that misses the set, right? But what do we know? What's our assumption here? We assume that every non-zero prime contains a prime element, right? I'll call it Z. So Z is in PX, but S also contains every prime element. That's controversial. So S must be all our stuff that can be written as either units or products of primes is everything that's not zero. So R is A. That is a very powerful theorem that just being able to say that every non-zero prime ideal contains a non-zero prime element, that gives you that everything that's not zero and not a unit factors uniquely in primes. I'm going to use this tool here. The following conditions. We've got 1 implies 2 implies 3. None of these are reversible in general, and I'll give you an example to show you can't reverse it once I'm done with the proof. So I'm going to go through and prove that Euclidean implies PID, PID implies UFD, and then I'll give you an idea of why they're not reversible. 1 implies 2. Suppose R is a Euclidean domain. I want to show that R is a principal ideal domain. So I want to show that every ideal in R can be generated by a single element. So let's pick one. Let's make the ideal not zero, because it's certainly zero is generated by a single element. Any ideas of what a good candidate? So if this theorem is correct, that ideal has to be generated by one single element. So now we are Colombo looking for what this single element would be. Any ideas on how we might find it? Well, what have I got? I've got that R is Euclidean domain. And what's the deal with Euclidean domains? What do they come with? Euclidean domains have that function that measures size, right? So that you can divide and find a smaller remainder, right? So consider our Euclidean function from R minus 0 into n0. Let's let S be the set of phi of alpha, where alpha is in I, but not 0. So I'm going to take this measuring function and I'm going to go through and I'm going to measure every stinking element of I except for 0, where it's not defined. All right. What does this give me? I don't know much, but this gives me a subset of the natural numbers, right? Because every one of these things barfs out a natural number, or is it? Right? Everybody agree with it? What's the big theorem that you know about? And of course, this is a non-empty subset because I'm assuming that I is a non-zero ideal. So I've got something to plug in there. So that's not an empty set. What do you know about a non-empty subset of the natural numbers? It's got a smallest element. If I agree with that, that's what we're going to do to pick this. So let's let alpha in I be such that there might be many choices for this alpha. I'll just pick whatever the smallest element of the subset is. I find an element in the ideal that made that value come out. I claim that I is generated by alpha. And that'll do it for me, because that'll show that every ideal is principal. Certainly, that must be true, because alpha is an element of I, and so the ideal generated by that element inside there, it's got to be a ideal inside there for sure. The interesting part is, why is this the whole shebang? Well, let's see. Let's prove this. let Z be an I. Now, what am I gonna do? Well, once again, the only reason this works is because this is a Euclidean domain. And what can I do in a Euclidean domain? I can divide and get a smaller remainder. Do I agree with that? So let's divide Z by alpha. I hope this divides in evenly. That's really what I'm going for, but let's see what happens. And we'll see, what am I gonna get? I'm gonna get Z is equal to R, well, of Q alpha plus R, with Q R and R 0 or P of R is less than P of alpha. Right? That's what the little Euclidean algorithm allows me to do. But there's an important observation, right? Rearrange this equation, I get that the remainder R here is C minus Q alpha. Agreed? And I don't know much, but I know that C is in I because I said so. And I know that this junk is in I because alpha is in I. So this is in I. Everybody agree with that? Therefore, phi R less than phi alpha is impossible. Why? That is right. Alpha was the element or an element in I that had a smallest phi value. R is in there. It can't have a strictly smaller phi value. So if this is not possible, what must happen? R must be C alpha just N. So if you've got the Euclidean algorithm, it has to be a principal ideal domain, period. Now, how about the next step? You're a PID and you're a UFD. Okay, so I'm going to give you kind of a little teaser before I do this. I gave a talk in Austria a couple of years back, and it was like a kind of a long general interest talk for this research group. But anyway, so I actually looked up some old papers. There was a paper written in 74 or 76 by a guy that didn't really do algebra. He was a logician, somebody that did mathematical foundations. This is a standard result you see in algebra, and one of the things that was proved in this paper is this implication cannot be proved in our axiom system without the axiom of choice. All right? So you cannot, I proved this without choice, there was no choice in the paper. But you can't do this one without the axiom of choice. So suppose I have a PID on proof to UFD. So let R be PID and P and R a non-zero prime. Right, okay, that's all. Since R is a PID, P is generated by some little b. Everybody agree with that? This is a theorem that we had a little bit earlier. That an element is prime if and only if it generates a prime ideal, right? So this non-zero prime contains a non-zero prime element. I've shown that any non-zero prime contains a non-zero prime element. Where did I use the axiom of choice? You were right not to answer because I didn't, at least not there. I used the axiom of choice here. This is where I used it. Now, you may not have seen, I didn't use it in that proof either because I used it as part of the proof. Do you remember when, part of the proof showing this implied this, where we used the fact that you can expand an ideal to an ideal that's maximal with respect to missing that said that that's where the axiom of choice was used. It's hidden, but it's in there. It shows this implication, and we've already done the heavy lifting earlier. So this makes the proof much shorter than, look this proof up. PID implies UFD in any standard algebra textbook, and you will get a mess because we already did the tough part earlier. Okay, any questions on that? Oh yes, I should give you a couple of examples, right? So I'm not just blowing smoke from it. I did say that none of the arrows were reversible. Well, example. There are tons of examples. UFD not PI. Okay, so I'm going to give you an example of a unique factorization domain that's our principal ideal domain. That's a principal ideal domain, right? So is UFD. This is a UFD not PI. I want to give you a theorem in a moment that tells you that this is in fact UFD. The fact that it's not a PID is easier to see. Consider the ideal generated by 2 and x in ZX. This is basically, this is the set of polynomials basically this ideal is all polynomials with integer coefficients, but I'm going to demand that the constant term is even. Okay. This is the smallest ideal that contains 2 and x. Let me briefly argue to you that this ideal cannot be generated by single elements, and that's why this is not a PID. So if this ideal is generated by a single polynomial, then f of x divides 2 and f of x divides x. Everybody agree with that? Because if there's a single generator, that thing must generate both the 2 and the x, right? Now, what conclusion, f of x divides 2, what can I conclude about the degree of the polynomial? I mean, you've got no choice but for the degree of f of x to be 0, right? That's it. So f of x is a constant. Right? And also, f of x must be either 1 or 2, right? Because the only constants that divide 2, the constants are the integers, and the only ones, well, and I really, if I want to be proper, I should say plus or minus 1 or plus or minus 2. Because the only constants in the integers that divide 2 are plus or minus 1, plus or minus 2. Well, it can't be plus or minus 1 because the rule of being in this ideal is a constant term has to be even, right? So it can't be this. And it can't be 2 because 2 doesn't divide x, right? Because that's the other condition, right? X over 2 is not in this ring. So that ideal is not principal. It can't possibly be generated with a single element. So that's a good example of a UFD that's not a PID. And in fact, it gets worse. In fact, if you have a UFD and you take a polynomial ring over any number of variables, it's still a UFD, but it gets further and further from being a PID. The ideals tend to get bigger and bigger as far as number of generators required. And in fact, I don't have to stop it in. I can make a polynomial ring and influence any variables, so it's still any questions on it? And there are many other examples. PID is pretty restricted. Euclidean's even more so. Finding domains that are PIDs but not Euclidean, that's a harder task. And in fact, I still see papers that are written occasionally about this, new constructions or new ways to do this. This is a special interest in number theory, as a matter of fact. And I'll give you, in one sense, the smallest example you can see in number theory. I'm not going to prove this works. It's complicated. It's too long, but it turns out that Z if you take the number 1 plus the square root of negative 19 over 2, and you adjoin it to the integer. So this is some crazy complex number. So this is the smallest ring that contains Z, and this crazy complex number is a PID, but it's not Euclidean. There are some number theoretic techniques that you can use to show that this is a PID, and to show that it's not Euclidean, you have to develop, the easiest way to do this is to develop this. Euclidean domains have these special things called side divisors, and you can show that this one doesn't have any, but it's not easy. Okay. Any questions on it? Let me give you kind of a big sweeping theorem about some of these properties and their behavior in polynomial rings. Theorem. Let R be the following problems. Are state with respect to polynomial. UFD. So that is to say R is a UFD, implies Rx is a UFD. So if you have a unique factorization domain, and so is its polynomial ring, you can continue this by induction to show that in any finite number of variables, the coefficient rings UFD. Noetherian. Criterion. That means again that all ideals are finitely generated, implies Rx is Noetherian. Note, if R is Noetherian, so is R power X. But if R is a UFD, R power X might not be. You can actually, you keep unique factorization in polynomial extensions, but not necessarily in power series extensions. The Noetherian is stable. Right? I'm going to go back with some of this if I can. Yeah, so I'm going to give you one more. This is kind of the last theorem that I want to give you. And then I'll come back and talk about some of this. One of the most important things that you can do is it's often very important to factor polynomials down. This comes up all over the place. And so it's important often to be able to tell when a polynomial can't be broken down any further, when it's already irreducible. Sometimes this is hard to tell, but here's a criteria that if you can get it, it's actually kind of a way to build irreducible polynomials. Let R be an integral. Domain. The quotient field K. And let f of x a n x n plus a n minus 1 x n minus 1 plus a1 x plus a0 be a polynomial in Rx. So all the coefficients, the AIs are all elements of R. If there exists if there's a non-zero prime in R such that E does not divide the leading coefficient. So it doesn't divide that, but it divides all the others. And E squared does not divide A0. So here's kind of this weird rule, right? E doesn't divide this one. It divides the rest. And you can't have the square of P divide this one. So you've got a limit on this one. This one, no P at all. This one, exactly 1 P. And the others in the middle have as many P's as you want, but at least one. Then The only proper factors of f of x have degree 0. All factors of f of x of degree less than n have degree 0. In other words, you can only pull constants out of this. All right. Additionally, if R is a UFD, then f of x is irreducible over the closure field. In AX. So let me give you an example here. Look at 3x squared plus 14x plus 6. This is, can anybody identify a prime that works like in the setup of the Eisenstein here? Can you find a prime that divides, actually, and let me do this here. I'm gonna go 84. Anybody identify a prime? Well, the problem is 3 divides the, you're close though. 3 divides this, so I can't use 3, but there's another. Well, let's be factors of 6, 3 and 2. So if this is Eisenstein, it can only be for the primes 3 and 2. 3 doesn't work here. But look at 2. 2 doesn't divide 3, right? 2 divides 6, but only to the first power, right? And 2 divides 84, right? So this is 2 Eisenstein. Is this polynomial irreducible over the integers? No, because you can pull out a 3. But that's what the theorem says. This is equal to 3 times x squared plus 26x. That's better. X plus 2. Right? And this polynomial is irreducible in the rationals. Why do we say that? But you said, but Jim, it's got a factor of 3. In the rationals, 3 doesn't count because it's a unit, right? Because there's a 1/3 in the rationals. So this is like invisible in the rationals in a certain sense. Everybody okay with it? So it's possible to have things that are Eisenstein for more than one prime. So example. Plus 6x squared plus 18. Notice this is 2 times 3 squared, so this can only be 2 Eisenstein. This. And this one is also 2 Eisenstein. And this is irreducible over ZX as well, because you can't pull any constants out of this because the first term is 1, right? And the greatest common divisor of the coefficients is 1. Here's another one that's Eisenstein. but it doesn't look like it first. Let's do this. My goodness, Jim, you must be drinking too many refreshing beverages out of aluminum cans because there aren't any primes that divide any of these coefficients, right? They're all one. How can this be Eisenstein? Well, sometimes you can do a clever change of variance. Look at replace x by x plus 1. Right? That's not going to actually, basically, that's just changing, replacing x by x plus 1. So that's not going to affect the irreducibility here. This becomes x plus 1 to the 4th. Right? And this is x to the 4 plus 4x plus 6x squared plus 4x plus 1. Now we're going to line it up here. X cubed plus 3x squared plus 3x plus 1. X squared plus 2x plus 1. X plus 1 plus 1. And this comes out to be x4 plus 5x cubed plus 10x squared plus 10x plus 5. And all of a sudden, after this change of variables, this is 5 as it's so. Then if you could reduce, so this polynomial is irreducible. So if f of x, the original, the one ball here, if that reduced, then that would mean that f of x plus 1 is g of x plus 1 times h of x plus 1, which would mean that that would reduce here. And we've shown that that can't be the case. Okay. Give you a lemma that is crucial in the proof that if R is a UFD, so is R of X. And given our time parameters here, I'll let you play around with that. I actually provide a proof in the notes if you're curious. See if you can prove it yourself. Let me give you the following lemma, and then we'll wrap it up with this. Whatever this is, 11 to 10. This is crucial or important in the proof that if R is a UFD, so is its polynomial ring. And like I said, I've got the proof in the notes if you want to see it. Let P be a prime element. Then P is also a prime. So if you have a constant that's prime in your coefficient ring, it's as a polynomial, it's also prime. And you're going to love this proof. I like short proofs. Look at Rx modulo the ideal generator of P. This is Rx modulo Px, which is isomorphic R mod B X. This R mod P is a domain. This implies R mod PX, which is isomorphic to Rx mod, the ideal term by P, is a domain. So P is prime in Rx. And there you go. Okay, I'll release you, but take advantage of your resources and get ready for the exam. Once my student, always my student. So if I can be of any help to you in the future, please let me know. And you all do well on the file, strong end, and have a great summer.